numbers are real, while some numbers are imaginary. Real numbers are probably still all the ones you were thinking of, so let's define imaginary numbers. Remember when we said that we can't take the square root of a negative number? In a certain sense, you can't, because there is no number that when squared will produce a negative number. However, in another sense, we can take the square root of a negative number if we admit that the result is imaginary. While the square root of 1 is simply 1, we will say that the square root of negative 1 is I. This is a lowercase I, always in italics, and it is the fundamental imaginary number. The square root of negative 4 would be 2i, because negative 4 is equal to 4 times negative 1. So this radical could be split up into root 4 times root negative 1, which is therefore 2 times I, or 2i. That covers imaginary numbers, so let's go back to the real numbers. Within the category of real numbers, there are two subcategories, rational and irrational. Rational numbers are defined as any number that can be expressed as the ratio of two integers. 3/2, 93/604. You just make a fraction, put any integer on top and any integer on the bottom, and you've got a rational number. The number on the bottom can also be 1, so all the integers themselves qualify as rational numbers. The only number that can't go on the bottom is 0, as that will yield a value that is undefined. Now, what are these irrational numbers? Given the definition of a rational number, clearly an irrational number is one that can't be expressed as the ratio of two integers. But what could these numbers be? Irrational numbers are ones that have non-repeating decimals that are non-terminating, meaning they continue forever with no pattern. The square root of 2 is such a number. If we plug this into a calculator, it will tell us that the answer is 1.4142, etc., etc., but no matter how many digits your calculator displays, it's not giving you the full story. This number extends forever, which means we can never list the square root of 2 as a decimal and be infinitely accurate, the way we can with 3/2. 3/2, or 1.5, is exactly 3 over exactly 2. If we try to approximate root 2 this way, we can get very close with something like 665,857 over 470,832. But it's not exactly right, and when we square this number, we get something just ever so slightly larger than 2. No matter how precise you try to get with this ratio, you will never quite get to the true value. Now you might be wondering, if we can't write out this number no matter what we do, doesn't that make this number imaginary? The answer is no. Nature is very clear in communicating to us that numbers like root 2 do indeed exist. If you make a right triangle that has legs with a length of 1, the third side will have a length of root 2. This triangle exists, so root 2 exists. It is a real number. It is simply irrational. When it was discovered by the ancient Greeks that irrational numbers must exist, all hell broke loose as it threatened the mystical notion that the world of numbers must obey a divine perfection. Other irrational numbers include pi, which is the ratio of the circumference of a circle to its diameter. We all probably know the first few digits of pi, which are 3.14159, yada yada yada. Again, this number never ends, with no pattern whatsoever in the digits. And it's not for lack of trying. Mathematicians have checked. With computers, we can calculate pi out to literally trillions of decimal places, and the numbers are random throughout. Once again, even though pi is irrational, it is a real number because circles are real, and all circles have a circumference. But we will get to triangles and circles when we start looking at geometry right after this.